All right, let's get right into it. Today we're looking at a pretty groundbreaking paper from NVIDIA that's all about a massive leap forward in how we train AI. This could really change the game.
So, to really get why this is such a big deal, you have to understand the sheer scale of the problem we're talking about. This isn't some program you can just fire up on your laptop. No way. Training a state-of-the-art large language model is, quite literally, one of the most computationally massive tasks humanity has ever attempted.
And how massive are we talking? Well, the numbers are just staggering. We're talking about needing tens, even hundreds of yottaflops of compute. A yottaflop, that's a 1 with 24 zeros after it. A septillion calculations every single second. It's a number that's so big it almost doesn't feel real.
And that cost isn't just about raw computing power. It's an enormous sink for time. For energy, the power bills are insane. And, of course, for money. This massive expense has basically built a wall, a huge bottleneck that's threatening to slow down the incredible pace of AI innovation we've all been watching.
So that leads us to the billion-dollar question that pretty much everyone in the AI world is trying to answer right now. How do we start tearing down that wall? How can we make training faster, cheaper, more efficient? But, and this is the critical part, without making the AI models dumber in the process. Right, so it all comes down to this fundamental trade-off. For a while now, the industry standard has been using 8-bit numbers, what we call FP8. They're reliable, they get the job done, but they're heavy. They use a lot of resources. The dream is to switch to 4-bit numbers, or FP4, because that would be way faster and way cheaper. The catch? Well, using smaller numbers means you get more rounding errors, and those tiny errors can stack up, make the whole training process go haywire, and leave you with a less accurate model. It's a real high-stakes gamble.
And this is exactly where NVIDIA's new paper comes in. See, they figured out that the answer wasn't just to invent a new, slightly better 4-bit number. No, that wouldn't be enough. They needed a whole system, a complete methodology to make 4-bit training not just doable, but actually stable and effective.
And what they came up with is what you could call their 4-bit stability playbook. It's basically 4 key techniques that all have to work together perfectly to solve that accuracy problem. So let's break them down one by one. Okay, first up is mixed precision. And this is just a really smart, pragmatic move. Instead of trying to cram the entire model into 4-bit, they find the most sensitive parts of the AI, which turns out to be about 15% of the network, and they just keep those parts in a higher, safer precision format. It's kind of like a sculptor using their superfine, high-detail tools only for the most delicate parts of the work, like the face.
Second, they pull out this really clever math trick called Random Hadamard transforms. So during training, you get these wild, extreme values called outliers that are really hard to represent accurately with tiny 4-bit numbers. This transform basically takes those outliers and, well, it kind of smooths them out, spreading their energy across other values, so the whole thing is easier to handle. Think of it like a smart photo filter that stops a few super bright pixels from totally blowing out the picture when you save it as a smaller file.
The third play in the book is 2D block scaling. Okay, so when an AI learns, information flows forward through the network, and then the error signals, the gradients, flow backward to make adjustments. Now the problem is, if a number gets rounded one way on the trip forward and a different way on the trip back, the AI gets confused and the learning breaks down. This 2D scaling makes sure that the numbers are represented the exact same way in both directions. That consistency is absolutely crucial for stable training.
And finally, we have stochastic rounding. You know how normal rounding always rounds 0.5 up? Well, over trillions and trillions of calculations, that tiny consistent bias can actually grow into a huge problem that throws the whole training off track. So stochastic rounding gets rid of that bias by rounding randomly. It's basically like flipping a weighted coin to decide whether to round up or down, so on average, it's perfectly fair and unbiased. Pretty clever, right?
So there you have it. That's the playbook, a super sophisticated 4-part strategy to make 4-bit training a reality. But theory is one thing. The real multi-trillion-dollar question is, does all this fancy stuff actually work under the brutal, real-world pressure of training a gigantic AI model?
And believe me, NVIDIA did not pull any punches with their test. They took a beefy 12 billion parameter model and threw an absolutely colossal 10 trillion tokens of data at it. According to them, this is the longest publicly documented 4-bit training run ever. This isn't some toy experiment in a lab. This is the real deal.
And the results? They're pretty jaw-dropping. Take a look at this chart. This shows the final validation loss. That's a measure of how many mistakes the model makes, so lower is better. On the left, you see the old FP8 standard, and on the right, the new NVFP4 method. I mean, look at them. The bars are almost identical. They got all that amazing efficiency with basically zero penalty to the final accuracy.
But okay, that's just one number. What about how the AI actually performs on real tasks? Well, this table compares the models on things like math problems, general knowledge, and common sense reasoning. And if you look at the numbers side by side, the scores for the old FP8 model and the new NVFP4 model are a near-perfect match. The AI is just as smart, just as capable.
And to put the final nail in the coffin, here's a direct quote from the paper. On a really important industry benchmark, their NVFP4 model scored 62.58% accuracy, and the original FP8 model, 62.62%. That difference is so tiny it's statistically meaningless. For all intents and purposes, it's a tie. They did it. They actually cracked the code.
So, what does this all mean for the rest of us? Well, it means AI development is about to get a whole lot faster and cheaper. It means AI is going to become way more energy efficient, which is a huge deal. It also means we can start thinking about building even bigger, more powerful models that were just too expensive before. And get this, on new hardware like NVIDIA's Blackwell chips, this could lead to a 2 or even 3 times increase in training speed. That's huge. Which really leaves us with one last, really exciting question to think about. For years, this insane cost of computation has been one of the biggest walls holding AI back. So if that wall just got a whole lot smaller, what kind of incredible breakthroughs, what new abilities are now waiting for us just over the horizon?